Hello. Thank you for the introduction. Thank you all for staying awake to the end of the day. So I'd like to talk a bit about some of the work I've been doing with passive acoustic mapping and how we can combine this with MR thermometry to improve our real-time monitoring of focused ultrasound ablation. So I don't think I need to tell this audience that MRI is fantastic and it provides excellent imaging and so is ideal for monitoring focused ultrasound because you can get great images of tissue, you can get temperature mapping, and that's great. However, MRI is also very slow and very expensive, and in particular, it can't detect cavitation, which is a really important factor for many focused ultrasound therapies, which could be things that you don't want, such as in blood-brain barrier disruption, or a thing that you do want, such as in ablation. So by adding real-time acoustic monitoring, in particular with acoustic mapping, we hope to get more robust monitoring of focused ultrasound therapies. So we've been testing this in a rabbit tumor model, which we sonicate with a single element focused ultrasound transducer, and we align beside that an ultrasound imaging array so that we can pick up the acoustic emissions from cavitation. We then put this whole assembly inside a 3 Tesla clinical MRI scanner, and we inject our rabbits with a phase shift nanoemulsion to promote cavitation, and this accumulates passively in the tumors. We then sonicate them, which causes the PSNEs to vaporize. This results in cavitation, which we can detect acoustically, and causes increased temperature rise, which we can pick up with the MRI. So to show you what this looks like, on the left there is an axial MRI image, and this is taken as a slice through the rabbit, so you can sort of see that drumstick-shaped thing is one of the rabbit legs, the blob in the middle is the tumor, and our ultrasound transducer is down at the bottom. And on the right is the corresponding ultrasound B mode image. So this, you can just see the outline of the skin surface. And when we do our experiments, I overlay on this our MRI temperature map and our passive acoustic map showing the cavitation. So if I start this video, so when we start our experiment, the focus transducer is turned off, so nothing's happening. And when we turn it on, we can immediately see that in the passive acoustic mapping data, and the temperature in the MRI thermometry starts to creep up. And this continues over the duration of the experiment, so the temperature gradually increases until we reach a critical point where the PSNEs will vaporize, and we can immediately see that with this violent cavitation showing up in our passive acoustic map. And what happens after that is you can actually see that the temperature, the slope of the temperature curve gets steeper because we're getting cavitation-enhanced heating. And then at the end of the experiment, we turn off our focus transducer, the temperature falls, and the acoustic emissions cease. So by comparing these modalities, we can see that we're getting focal heating from the MRI. We can also see we're getting focal cavitation from the cavitation mapping. And by comparing the two, it's pretty obvious that there was significant cavitation-enhanced heating in this experiment. So we then looked at how these two modalities compare in a parametric study. So we varied both the ultrasound power input and the duration of the exposure. And as you might expect, as you treat for longer or you increase the ultrasound power, then both your maximum temperature rise and your maximum cavitation energy increase. And the two are well correlated pretty linearly as well. So in some circumstances, with sufficient calibration, you might be able to do without the MRI and just use ultrasound monitoring. We also looked at the effects that the PSNEs had on their own, so we compared rabbits that were injected with these PSNEs to promote cavitation to rabbits that weren't. And in this case, there was an exponential increase in the acoustic emissions and roughly doubling in the maximum temperature rise. So to conclude, I think I've shown that passive acoustic mapping and MR thermometry can be useful when used together to monitor focused ultrasound ablation. The PSNEs may be used to promote cavitation, which then increases the temperature rise, making the therapy more effective. And in future, I hope to use this to optimize the control and results of cavitation-enhanced ablation. So with that, I'd like to acknowledge the people in the focused ultrasound lab that helped me with this work, my collaborators at BU, and my funding. Thank you.
Questions from the audience? I have a quick one. In that curve you were showing where the temperature was rising and then there was an inflection once you got your cavitation, if there had been no cavitation, what would the temperature have reached versus what did it reach with the cavitation? How much of a delta was there? Do you have a sense of that?
Yeah, so we actually did this parametric study over kind of 9 different conditions with and without PSNEs, and at the optimum point, it was about 20 degrees difference. At where you're not at the optimal point, then the gap gets smaller. So yeah, depends.
Interesting.